Yes, Anna. Anna, in my session, session is about to start. That's fine. That's fine. Bye. Good evening, everyone.
Good evening, sir.
Yeah. So we will start the class within 2 minutes. Okay. We will wait for some more time, and we will start the class within 2 minutes. So shall we start the class? I'm sharing my screen.
Yes, sir.
Yeah. So is my screen visible?
Yes, sir.
Yeah. So in the last class, we have seen about elongation of circular sections under axial loads and the matrix representation of stress and strain and the relationship between elastic constants. Okay, and we have also seen about uniaxial and triaxial state of loading. So in today's class, we will see about impact loads and the axial deflection of members having varying cross sections, then about statically indeterminate bars, and then elongation and stresses under self weight, and temperature stresses that also we will see, and we will wind up with the strain energy. Okay. So I have asked you to solve this problem, right? Has anyone solved this problem? Hello, am I audible?
Yes, sir.
Yeah, has anyone solved this problem? Is it difficult to solve or should I solve?
No, sir. Not that difficult, sir.
Okay. So shall I skip this and continue with the today's lecture?
Yes, sir.
Okay. Yeah. So today we will see about impact loading. Okay. So what do you mean by impact loads actually?
Falls from any certain heights.
Yeah. Can you please more clear? Can you please be more clear? Hello.
Yes, sir.
Yeah. Impact loads are loads which are applied suddenly. Okay.
Which are applied suddenly or pass from a heights.
Yeah. So gradually apply. Till now we are actually seeing a gradually applied load, which means like we are giving some time to apply the load. Whereas impact loads means like we are suddenly applying the load. Okay, or the external force is suddenly applied. Okay. So in this we will do one problem, and based on that we will learn the concept. Okay. So here we have to determine the maximum deformation of spring if the spring constant value is equals to 500 Newton per mm and the load which is being applied is 5 kilonewton and the distance of this load which is made to fall over this small bar is actually 20 mm. Okay, this height is equals to 20 mm and this weight is actually made to fall from a height of h. Okay, which is where W is equals to 5 kilonewtons. And here is a spring which is of spring constant 500 Newton per mm. Okay. So in impact loading, the basic formula is like we have to find out first the delta static. Okay. The deflection due to considering the W as a static load. Okay. So when we consider W as a static load, how can we find the deformation of this spring delta? Can anyone say the relation between the force which is applied and the spring constant and deflection?
Stiffness equal to load by amount of deflections.
Yeah. So
F
stiffness.
equals to kx.
Yeah, F is equals to kx. Yeah. So k is equals to F divided by delta. Okay. So this is for us static. If the load applied is a static load. Okay. So from this we have to calculate the delta static. Okay. So delta of static load, imagining like W is applied as a static load, okay, which is equals to W divided by K, okay. So W here I am substituting this W in terms of Newton, 5 into 10 power 3, and the K which is given by 500 Newton per mm. Okay. So what is the value of delta static I would be getting?
10 mm.
Yeah, 10 mm. So once I have find out the delta static, the objective of this problem is to find out what is the deformation under the impact load, which I name it as delta impact. Okay. So in order to find out delta impact, first I have to find out the impact factor. Okay. And then what I will do is like delta impact can be found out by delta static into impact factor. Okay. So the impact factor, how I will find out is like this is the formula for finding out the impact factor. Okay. 1 plus root under root 1 plus 2h divided by delta static. Okay. So can you find out the impact factor and say what is the impact factor? 1 plus under root 1 plus 2. What is the h here?
20 mm.
Yeah, 20 mm divided by delta static is 10 mm. Can you find out the impact factor and say?
3.23.
3.23. Yeah, 236. So once we have find out the impact factor, then we can calculate the deformation under the impact loading as delta impact is equals to impact factor into delta static. Okay, which means like 3.236 into what is the delta static? 10 mm, which is actually nothing but 32.36 mm. Okay, is this clear?
Yes.
Yeah. So similarly, if you want to find out sigma impact also, you can directly apply this same formula like impact factor into sigma static. Here we can't actually find out the stress, but if this spring constant is actually replaced by a tapered bar, then you can actually find out the sigma impact. Okay. So moving on to the next slide. So can you find out the axial deflection of coming to the axial deflection of varying cross-sectional bars? Uh, do you know this? Has Yasdeep already taken this, or shall I skip this and move on, or should I have to take this?
Skip, sir.
Is everyone okay with skipping this problem?
Yes, sir.
Okay. So now we will come to statically indeterminate bars. Okay. So what is meant by statically determinate and what is meant by statically indeterminate?
So statically means
Basically,
means
determinate means the system is equilibrium.
Okay, the system. See, most in strength of materials, we deal with equilibrium systems only. Okay.
Yes, sir.
So statically determinate means can you be more precise? Statically determinate means like for example, based on the force balance, I can find out the value of the externally applied loads or the reactions of the supports. Okay. Whereas for statically indeterminate bars, I can't find out the reactions explicitly. Okay. What I told now is clear to you all.
Yes,
can
sir.
you repeat once.
Yeah, for example, in this previous example, if you see, this is a statically determinate member. For example, if I want to calculate the value of P, what I should do?
Balance the force.
Balance the force in x direction.
Yeah, balance the force in x direction. I can simply calculate the value of P. Okay. Whereas here, can I do this? Or under which conditions this will be a statically determinate load? For example, here the force is 20 kilonewton. Okay. So whether under what conditions this will be a statically determinate structure, and under what conditions this is going to be a statically indeterminate structure. See, I have given you a loading of 20 kilonewton at the junction of between these two bars. Okay. So under what condition this is going to be a statically determinate structure? Anyone? Okay, I will explain this. Okay. So for example, this gap I have mentioned it here, right? So if the delta L of this composite bar, okay, considering 1 and 2, okay, if the delta L of this composite bar is less than or equal to the gap, okay, what happens here? There will be a reaction, okay, which I am naming it as A, and here this point I am naming it as B. So if delta L of this composite bar, if it is less than the gap, okay, then what will happen to this reaction force? How I will calculate? Or what will be the value of reaction force?
20 kilonewton.
Yeah, the reaction force will be 20 kilonewton, and this will be a statically determinate. Okay. And what can I say about RA, which is equals to 20 kilonewton? Okay. But what happens if delta L is greater than this gap? Do you think any reaction will be turning out, or any reaction will be arising at point B?
Yes, sir. Upward reaction is occur at the point B.
Yeah, reaction will occur at point B. Okay. So this I'm naming it as RB. Okay. For example, now we will first find out whether delta L is actually greater than or equal to the gap. I mean, less than or equal to gap, or delta L is actually greater than gap. Okay. So initially, what load I have applied? 20 kilonewton. So initially, if I take the free body diagram of this bar one, okay, here I have applied 20 kilonewton. Okay, the reaction force will also be what? 20 kilonewton for statically determinate structure. Okay. So delta L of this and for the free body diagram of member 2, what is the force acting on member 2 here?
20 kilonewton, sir.
No. See here when I take a cross section here, okay, and I see the forces which are acting above and this side, what will be the value of this force which is acting on this cross section?
20 kilonewton per weight of first part.
No, here I am not considering the self weight actually. Here, what I am considering is like 20 kilonewton as a point load, externally applied load. Here I am considering. Okay. So the first member is actually acted upon by a tensile load of 20 kilonewton, whereas the second member, the axial or the externally applied point axial load is actually 0 kilonewtons. Because this 20 kilonewton is balanced by this reaction force, right?
Yes, sir.
Yeah. So the force in member 2 is actually 0.
Yes, sir.
Agree?
Yes, sir.
Is this clear to everyone?
Yes, sir. Clear.
Okay. So delta L of this composite bar will be equal to PL by AE. Okay, P1 L1 divided by A1 into E1. Here, since the both the areas are different, I am taking PA1 L1 divided by A1 into E1. Okay, plus P2 into L2 divided by A2 into E2, which is equals to, here P1 is actually what, 20 kilonewtons, right? So I am converting this to Newton. And what is the value of L? 500 mm. Hmm?
Hmm.
And A what value I have given? 200 mm square into E1. E is actually what? 100.
Then
Uh,
power.
yeah, 100 gigapascal. So I am converting this to megapascal. Okay. So what is then P2 is actually what?
0, sir.
Yeah, 0. So ultimately, what delta L are you getting? Can you find out and say?
0.5, sir.
Yeah, 0.5 mm. So this 0.5 mm is greater than gap, right? So delta L of bar is greater than gap. So this becomes a statically in yeah.
Sir, actually, will you be able to substitute the units as itself directly?
Yes. See, if I am interested in getting the delta L in terms of mm, what notation I will follow is like I will keep the value of force as Newton, and I will keep the Young's modulus value as in megapascals itself. And area, length, all I will be substituting it in mm so that the result I will be getting it in mm because
Then
megapascal
force
is
is in
actually
Newton.
yeah, force is in Newton and E value is in megapascal, which is nothing but Newton per mm square.
Okay.
Okay, so the result I will be getting it in mm.
Okay.
Yeah. So since delta L of bar is greater than the gap, so this will be a statically indeterminate member. So there is a reaction which is termed as RB. Okay. So what I should do? So if I am getting see why I have introduced for example the net axial load which is acting is 20 kilonewtons, right? Okay. So what I will be doing in statically indeterminate bus or for any kind of statically indeterminate system, what I will be doing is like I will introduce the unknown forces opposite to the direction of the net axial load. Okay. Here the net axial load is towards the downward side. Okay. So what I'm doing is like I will be introducing two reactions like in the opposite direction to the net axial load. Okay. So the force balance will be what? RA plus RB plus, I mean, minus 20 equal to 0. Is it correct?
Yes,
Yes,
sir.
sir.
Yeah. Here the unknowns are RA and RB. So only we are saying this as a statically indeterminate structure. Okay. So from this, I will get RB is equals to 20 minus of RA. Okay. So the next step, what I should do? Anyone?
Substitute the RB equal to 20 minus RA, sir.
Okay. In which I should substitute actually?
First formula, sir. RA plus RB minus 20.
Yeah. See, if I am substituting that, I will not. I won't since RA is also unknown, right?
Yes, sir. Yes, sir.
Yeah. So I won't be getting the answer. So what I will do is like, see here delta L of 1, okay, which is the elongation of or the deformation of the first bar plus delta L of 2, which is the elongation of the second bar equal to what is the constraint here? Gap is the constraint here, right?
Yes, sir.
Yeah, so the whole deformation of this combined system can be equal to this gap. Okay,
Yes, sir.
yeah. So which in turn I can write it as RA. Here RA is actually unknown. In the last thing, if for statically determinate, we substituted RA equal to 20 into 10 power 3. I mean, which means 20 kilonewton. Here, both RA and RB are unknown here. Okay. So, what I will do, I will substitute RA and what RA into 500 divided by 200 into 100 into 10 to the power of 3 plus what is the delta L of second bar? It's actually RB, right?
Yes, sir.
So what can I write RB as? 20 minus or RA minus 20, I can write it, right?
Yes, sir. Resultant in upwards.
Yeah, because this is in the downward direction and this is in the upward direction. So what can I write? 20, I mean RA minus 20. Okay.
Into 500 by.
Yeah. Imagining this as a tensile load. Okay. Imagining this as a tensile load. Since RA is in the upward direction and 20 is in the downward direction, so I am writing it like this. Okay. Any doubts here?
Sir,
Yeah.
sir, we are writing del L, the first formula, del L less than or equal to gap statistically determinant, right, sir?
Yes. Yes.
But this condition is that statistically indeterminate. Then why substitute the equal to, sir? I mean, del 1 plus del 2 equal to gap.
Yes. Actually, what happens here is like
Uh,
you can't exceed beyond this gap, right? Only the permissible deformation is equal to gap. Okay.
yes, sir.
After that, what will happen? The support which is at B, right? It will actually exert a reaction so that you will get a force on this second member.
Okay, sir.
Yeah, till for statically determinate there is no force, but whereas when you calculate delta L of this combined thing, what it
Yes,
turns
sir.
out, the value is actually greater than the gap. So in reality, the combined deformation of this cannot be more than the gap. So only the reality is like delta L of 1 plus delta L of 2 equal to gap.
Okay, sir. But the condition is statistically, I mean, greater than, right, sir?
Yeah, the condition is, yeah, it is, since it is greater than of gap, then we are actually equating it to gaps so that we can find out the reaction forces RA.
Okay, sir. Yes, sir.
Okay. Yeah.
Yes. Sir, and one more. Why we
Yes.
substitute del L equal to RB?
Here for del L of 2, right?
Yes, sir.
See, for example, here what is happening is like, for in the first member I assume the reaction as RA. Okay.
Yes, sir.
So the downward force will be matched with RA.
Yes, sir.
So since this is a member is in tension, so I am writing it as a positive value RA into 500 divided by like this. Okay.
Yes,
Whereas for this second member, I am still considering RA to be acting upwards, which is a tensile load, and whereas this 20 kilonewton is actually acting in downward direction, which is a compressive load for member 2. So
yes,
only I
sir.
am writing RA minus of 20, which is equals to RB.
Yes, sir.
Okay.
Okay. Okay. Okay, sir. Okay, sir.
Yeah. Into what is the length? 500 divided by the area is A by 2, right? So 100 into E. E is 100 into 10 to the power of 3. So can you find out the value of RA from this? Can anyone say what is the value of RA?
Newtons.
4010 newtons. No. Yeah, 4010. See, you are approximately, yeah, correct. I mean, RA should, no, actually, RA should be equal to 16 kilonewtons. Is somebody getting this answer?
Yes, sir, 16 kilometer.
Yeah, RA should be equal to 16 kilonewtons. Is, is everyone getting RA equal to 16 kilonewtons?
Sir, one doubt.
Yeah.
So actually, it must be RA minus 20 into 10 power 3. No, sir.
No. See, actually, RA minus 20 into 10 power 3 is actually, yeah. See, from here, what I will be getting is like, I will be getting the value in kilonewtons, okay? If I substitute into 10 to the power of 3, then you can say in newtons.
Yes, sir.
Okay. Whereas here I have imagined RA to be in kilonewtons. So the output value what I will be getting is kilonewton. Okay. If I am not including this 10 to the power of 3.
So, but you told like the force should be usually in Newton and
Yes, see, if I am
length should be
substituting
in.
the force in newtons, then here I should put 10 to the power of 3. I should multiply by 10 to the power of 3. So since I haven't multiplied here 10 to the power of 3, I can directly say RA in kilonewtons. Okay.
Yes.
Yeah, this is all convenient to your unit system. Like in which unit you want to play with, you can play like that. Okay.
Yes.
Yeah. So this value of RA will be equal to 60 kilonewton. Since I am getting a positive value, so the direction of RA is as assumed, which is in the upward direction. Okay. So what will be the value of RB and in which direction it will be acting? RB is actually 20 minus RA, right?
4, sir.
Yeah, 20 minus 16, which is equals to 4 kilonewton. And in which direction?
Upward.
Yeah, upward
Upward
direction.
direction.
Yes. So RB is equals to 4 kilonewton and RA is equals to 16 kilonewton. Okay. So this is the general methodology to actually solve a statically indeterminate structure. Sorry.
Sir, in
Yeah. Yes. Someone was about to ask a doubt, right? Okay. So shall I proceed?
Yes, sir.
Yeah, so the basic methodology in solving a statically indeterminate structure is like first calculate the net reaction force. Okay, first calculate net reaction force, which means like even if I am giving here another one force, say for example 10 kilonewton, then 20 minus 10 will be equal to 10 kilonewton. Okay, first calculate the net reaction force and then see in which direction it is acting. Here, for example, this is acting in the downward direction. So introduce the reaction or the unknown forces in a direction opposite to the net reaction load. Opposite to the net reaction load. Okay. And then solve this compatibility condition, which means like delta L of this composite system must be equal to either 0 or either equal to gap. Okay, for example, here if I am not giving any gap and I have considered this as the rigid support, then I will substitute delta L of this composite bar, which is equals to delta L1 plus delta L2 equal to 0. Okay, and then I will find out the unknown forces. Okay.
okay.
Yeah. So this is the general methodology for solving a statically indeterminate bar, which is very important for gate. Okay. If you have any doubts, you can ask me. Or if something is not clear, also you can ask me. Okay. The basic extension from this problem is like you can find out the axial stresses which is acting in each member, and from that you can actually find out the maximum stresses acting in this system. Okay. Can you find out the maximum? Can you find out the stress in member 1 and stress in member 2?
Yes, sir.
Yeah.
Yes, sir.
Stress in see here. Here I am working out. Okay. Stress in member 1, which is actually equal to P1 divided by A1. Here, what is the value of P1?
15 minus 20.
20 minus RA.
Yeah, no, in member one, in member one is actually
15.
equal to RA, right?
15.
Because you have RB equal to 4 kilonewtons. So when you take a cross section here, okay, and if you find and if you balance the forces in the upward as well as in the downward side, here in the upwards, like RA equals to 16 kilonewton, which is a tensile load, and in the downward, here 20 kilonewton is acting downwards and 4 kilonewton is acting upwards. So 20 minus 4, which is equals to 60 kilonewton, which is actually acting downwards for member one.
Yeah, okay, sir.
Yeah, getting it or not? Huh?
Yeah, sir.
Yeah, fine. So 16 into 10 to the power of 3. Here I am substituting the value of force in Newton, and area I will substitute in mm square. Okay. So the final value what I will be getting?
18 Newton per mm.
Yeah, 80 Newton per mm square, which is nothing but 80 megapascal. Okay. And this is a tensile stress or compressive stress, which is acting in member one.
Tensile stress.
Yeah. Again, for member two, I am working out here. Okay. For member two, when you draw the free body diagram of member 2, okay, in the up, what is acting? 16 kilonewton is acting upwards and 20 kilonewtons is acting downwards. So the net load is 4 kilonewton, which is acting downwards, right?
Yes.
Yeah, and in the downward, I am seeing this cross section, right? Okay, I am seeing this cross section. And in the downward direction, 4 kilonewton is acting upwards. So this is a tensile load or compressive load for member 2?
Compressive load, sir.
Yeah, compressive load. So I will introduce a negative sign and I will, or else like I will introduce a positive sign and I will write compressive. Okay. So 4 into 10 to the power of 3 divided by what is the value of the area, which is 100 mm square. So sigma 2 will be equal to how many megapascals?
40.
Yeah, 40 megapascal, which is a compressive stress. Okay.
Sir,
Yeah.
sir, kindly repeat first, I mean, stigma 1, sir. How to find the force on first bar?
Okay. How to find the force? See, maybe I will show the example with this. Okay. How to find the forces on each member. Okay. Since both are related to each other, I will show it here. Okay. And then I will show it for that statically indeterminate structure also. Okay.
Okay, sir.
Yeah. So for example, here if I calculate the first, I will calculate the value of P based on the equilibrium of forces. Okay. So 10 kilonewton is acting this side. So this I will the force which is acting towards this side, I will take it as positive value. Okay. So 10 force acting on whereas which side it is acting? P is acting towards this side, so I will take this as minus P. Okay. And 40 is acting this side, so I will take as plus 40, and 16 is acting towards the direction of P, so I will take it as minus 16 equal to 0. So what is the value of P here? 50?
34.
Yeah, 34.
34, sir.
Yeah. So 34 kilonewton. So then I have to find out the force on each member, right? So for that, what I will do, I will create cross sections areas for each member in the
Excuse me.
in between. Yeah.
So can you explain the sign convention, how you took minus P and plus 40?
Okay. See, actually, what I am imagining here as the sign convention is like all the tensile loads are positive. Okay, and all the compressive loads are negative. Okay. So here for this 25 mm, since this is acting towards this side, which is actually we can imagine this as a tensile load, right? For this member one.
Yes, sir.
Yeah, so I am considering this as a positive value. So the whatever the direction of force which is opposite to this 10 kilonewton, I will take it as a negative value because this 10 is I assumed this as a tensile load for this member one. So whatever the direction which is opposite to this 10 kilonewton, I will take it as a negative value. The sign convention is clear, or should I have to repeat it? See, here I have since I have taken whatever the values of the loads which is acting towards the left hand side is as positive, which I am imagining this as a tensile load. So I am taking this convention as positive. Okay, so 10. Here, if you see, it is acting towards the right hand side, which I am imagining this as a compressive load. So I am putting as minus P. Then again, here 40, which is acting towards the left side. So I am taking it as a tensile load and I am substituting plus value. And similar for 16, since it is acting towards the right hand side, I am taking it as a 16. I mean minus 16. Okay. You can imagine like this, like whatever see for a what to say, for a horizontal member, whatever the forces which are acting towards the left hand side, I am taking it as a positive value, and whatever the forces which are taking it as a right hand side, I am taking it as a negative value. You can also interchange the sign convention. Okay, whichever is what to say convenient for you, you can take the sign convention according to that. Okay,
Yes,
here
sir, got it.
here what I can do, I can also take the forces towards this as a negative value and I can substitute it. Still, I will be getting P value equal to 34 kilonewton. Okay,
Okay, sir.
yeah, but what is more important is like you have to identify within each member what is the type of load, whether it is tensile load or compressive load. That is more important. For finding out the value of the unknown forces using force equilibrium, you can assume any direction and any sign convention according to your convenient. But when you are set according to a particular sign convenient, like you have to follow the same sign convention through the system. Okay.
Yes.
Yeah. So what I have done here is I have calculated the unknown force P is equals to 34 kilonewton. Now I am taking for each member what is the value of load which is acting on each member. Okay. So the methodology for finding out the member for finding out the force acting on each member is like, see, first I will take a cross section in between for each member. For example, for let us name this member 1 and I am taking a cross section in between. Okay, so here since this is a bar which is in equilibrium, the left hand side forces must be balanced with the right hand side forces. Correct, na?
Yes, sir.
Yeah. So in the left hand side, what force I am getting? 10 kilonewton towards the left. Okay, whereas in the right hand side, what force I am getting? 34. Okay, minus 40 plus 16. Okay, which is actually 10 kilonewton towards right side. Okay, here I am following the sign convention, like force in this side is positive. Okay, so 34 I am writing it as positive, minus 40 plus 16 equals to 10 kilonewton, which is acting towards this side. So when I draw the free body diagram of member 1, what it will happen is it will look like this: 10 kilonewton acting towards the right side, and for this section 10 kilonewton is acting towards the left side. Is this clear? Excuse me.
Yes.
Yeah. So this is a tensile load for member 1. Okay. So now
Yes,
coming
sir.
to member 2, what I will do is like, again for member 2, what is the value of force acting on this side? 10 minus that. Now what I am considering is like, whatever the value of forces which is acting here is positive. Okay. So 10 kilonewton is positive and minus 34 kilonewtons. Okay, which is equals to, what is the value of this force? This is like 40 kilonewton towards this side and minus 16 kilonewtons, which is equals to that, I mean 24 kilonewtons compressive. Okay, Is this clear? See, minus 24 I am getting towards this. So it will be 24 kilonewtons towards this. Or else you can term it from your intuition also. See, 10 kilonewton is acting towards this side, and 24, I mean 40, what is the value of P? 34 kilonewtons is acting towards this side. So the resultant force will be 24 kilonewtons, which is acting towards this side.
Yes.
Fine?
Yes, sir.
Yeah.
Sir.
Yeah. Then for this member, for this third member, again I am drawing a free body diagram, and then 10 kilonewton is acting towards this side, and 20 40, I mean 34 is acting towards this side, right? So the effective stress will be 24 acting towards this side, and then I am having a 40 kilonewton which is acting towards the left side. So 24 minus 40, which will be 16 kilonewtons acting towards the left side.
60 kilonewtons to right.
Yeah, here this side it is only one load, so 16 kilonewtons towards the right side. Is this clear?
Yes, sir.
Yes, sir.
Yeah.
Yes.
So it's actually a balancing of forces for each member, for finding out the loads acting on each member. Okay. From this you can find out what is the stresses in sigma. I mean member one. What is the stress in member two? What is the stress in member three? Like that. Okay.
Okay, sir.
Yeah. So, let's proceed to the next topic, which is based on axial loads. Okay. So here, actually, I have seen Yasdeep video, and here he has also discussed some points on stresses and axial deformation, right, due to self weight. Is it so? Should I have to repeat it once again, or like can I can I repeat it very fastly?
No, sir. Continue.
So did you show this video in first lecture?
No, this video I haven't shown in first lecture. This is the first time I am taking this axial stress. Whereas like the person who was handling SOM before, like he has taken axial stress and he has solved what is the elongation and what is the stress value, like that. So if you want to repeat it, I will repeat it once again very fastly. Okay?
Yes, sir.
Yeah.
Please repeat.
Yes,
Yeah.
sir.
Okay. So see here first I am considering a cylindrical bar, okay, which is of area A, which is of cross sectional area A, and which is of length L. Okay. So this is having a self weight which is equals to W. Okay, this W I am terming it as a self weight, and this weight I can write it as mass into gravity, right? Mass into gravity of this member. Okay. So mass I can write it as rho into volume of this member, which is nothing but AL. Here rho I will be replacing it by gamma. I mean sorry, rho AL into G. Okay.
Oh, yes, sir.
Yeah. So this is the total weight of this member. But I'm here terming a new term called weight per unit volume. Okay, which is denoted by gamma, which is nothing but weight per unit volume, which is nothing but A into L, which is nothing but rho into G. Okay, for convenience. Then what I will do is like, for example, due to self weight, what will be the load acting at this tip of this cylinder? Can anyone say what is the load which is acting on this tip of this cylinder only due to self weight? Here I haven't given any external load. Okay.
Will total mg means rho alg.
No, due to self weight only at the tip. For example, see, 0. Yeah, here the W value will be equal to 0, since I don't have any material which is below this. Okay, for example, you can imagine your whole what to say human body, and then like you can take the excuse me. So you can take the knee part. Okay, for example, the knee part will be feeling the weight of your body part which is below your knee. Okay, so here the bottom fiber will be experiencing no load, zero, whereas the top fiber will be experiencing the full load, which is equals to W is equals to M into G, which is nothing but gamma into A into L. Since I have considered gamma to be weight per unit volume, okay, this is weight per unit volume, gamma.
So can we say reaction force?
Yeah, see, actually the reaction force will be equal to W. Okay, but for example, if I'm taking a cross section here, okay, and I'm finding out the value of the load WXX which is acting here. What can I say about this? Imagine this length to be X, okay, and I am calculating and I want the WXX or the load acting at this cross section. What will be the value of WXX? Can anyone say?
Gamma into axis.
Yeah, gamma into A into X,
X.
capital X, I mean small x. Okay. So like that, if I go on increasing the value of X up to L, then here only I will be getting the whole value gamma into A into L, which is the weight of this whole member. And that weight of the whole member will be acting as the reaction force at this fixed support. Getting what I am saying?
Yes.
Yeah. So when I draw the loading diagram for this or the variation of load for this member, how it will look like?
Maximum at the top.
Yeah, maximum at the top and minimum at the bottom. I mean zero at the bottom. Okay, and in between it will be varying linearly. This is a linear variation. Okay, so at the top it will be W equal to gamma into A into L, and at the bottom it will be zero. Okay, getting what I'm saying?
Yes,
Yes.
sir.
Yeah. So then, if you want to find out the stress at each cross section, do you think the stress will be varying at each cross section or it will be constant at each cross section?
It will vary.
Yeah, it will be
Varying.
varying since the load is varying. Okay. So, for example, sigma axial, which is axial stress at any cross section, will be given by Wxx divided by Axx. Here Wxx is actually nothing but gamma into A into X, which is the load at any cross section, right? For example, if I take the cross section here, what will be the load at this cross section? Gamma into A into X. Here if I take this as the cross section, okay, what will be the value? Gamma into A into X, the where X actually changes from here to whole direction. Okay. So gamma AX divided by here A is actually not changing. So A and A cancel. So what it ultimately turns out? Gamma into X. Okay. So can you tell where the maximum stress will actually occur?
At the top.
Yeah, at the
A
top.
bit long.
Yeah, the maximum stress will occur at the top. So sigma max will occur at X is equals to L, which is nothing but gamma into L. Okay. Then I am going to the calculation of deformation. Or this gamma L can I can rewrite in terms of W as gamma is W by A into L, right? W by A into L into L. And here L and L cancel. So sigma max at X is equals to L, which turns out to be W by A. Clear? Okay, in terms of load I have written, or the self weight, I mean self weight I have written. Okay. Now I am proceeding to the deflection or the deformation due to the self weight. Okay. So deflection delta L is equals to Pxx into dx divided by Axx into Exx. Here it is made of same material, so I am taking it as E and I am integrating it from 0 to L. Okay. So here what is the value of Pxx? Gamma A into x. Okay. Into dx divided by, here since area is not changing through the cross section, so I am writing it as A into E. So integrating it from 0 to L. So what will be the value I am getting here? Gamma into x square by 2. In limits I am applying it from 0 to L. So gamma L square divided by 2.
So E.
2E. Yeah, 2E. Okay. So in terms of W, if I am writing, what I should do? I should write it as W by AL into L square divided by 2E, which turns out to be WL by 2AE. Excuse me. So this is the axial deflection due to self weight. Okay. Is this clear?
Yes, sir.
Yeah. So now before going to this, what I will do is like I will tell the axial deflection due to a conical bar. Okay. And then I will come to this problem. So due to conical bar, for example, I am having a conical bar, okay, like this, and this is fixed support, okay. Now this has a diameter of d, okay. For example, if I imagine the same a cylinder of diameter d, what will be the value volume? It will be A into L, right, which is pi by 4 d square into L. This will be the volume of a cylinder. Okay. Here I am considering a conical bar. So what will be the volume of a conical bar?
1/3.
Yeah, one third of a cylinder. Yeah. So what I am imagining is like the load value which we have assumed as gamma AL, right? For a cylinder. For a cone, it will become as gamma AL divided by 3. Okay. And this will act at the top, whereas at the bottom it will be 0. Okay. Then I will find out the value of, see here the area of cross section is actually changing, right? At each cross section the area is actually changing. So I need to find out the value of AXX, which is nothing but it is consisting of circular strips of diameter DXX. This is correct or not? Pi by 4 dx square. I can write it like this, right?
Yes, sir.
Yeah. Then dxx can be written as this whole d into x divided by L. I can write it like this, right?
Yes, sir.
Yeah.
Yes, sir.
For example, here I am imagining x equal to 0 and here x is equals to L. So I can write dxx as d into x by L. Correct? So I am rewriting this as d square into x square divided by L square. Okay. So
So
again,
how you can write the dx by L?
this, okay, how I have written dx by L. See, for example, at x is equals to 0, diameter d equals to 0. At x is equals to L, diameter d equals to d. Okay. So if I write using the straight line equation, for example, the at any section I want dxx. Okay. So dx y, which here I am taking dx as y minus y1. Here y1 is actually what? 0. divided by y2 minus y1, which is y2 is actually d minus 0, which is equals to x minus x1. X1 is actually 0 divided by x2. X2 is L minus x1. So dx is equals to d into x by L. Since the diameter is varying linearly, I can write it using a straight line equation. Like interpolation I can do. That is the thing I have done here.
Okay.
Okay?
Yeah.
Yeah. So the area I can write it as this pi by 4 d square, I can write it as the area of this cylinder. Okay, so I can rewrite this as a into x square divided by L square, or the area which is at the top. Okay, area of the top fiber, pi by 4 d square. Okay, now I'm imagining a cross section here at a distance of x. So what will be the value of load W, or what will be the value of load gamma into AXX into,
X by 3.
yeah, into x divided by 3. Okay, so when I'm rewriting this, I will substitute the value of AXX in this term. Okay, so gamma into AXX, I can write it as a into x square into x will become x cube divided by 3 into L square. Okay, now when I'm multiplying and dividing by L, I can write this in terms of W. Okay, which I can rewrite it as, for example, gamma A into L divided by 3. I can write it as W into x cube divided by L cube. Okay, this will be the variation of the self weight along this conical member. Okay, so if I want to draw the loading diagram or the axial loading diagram, how it will look like? It will look like W into x cube by L cube, which is a cubic parabola. Okay, here I will be having gamma AL divided by 3, and this curve will follow this equation Wx cube by L cube. Okay, you are getting what I am saying?
Yes, yes.
Is everything clear, right?
Mm-hmm.
Yeah. Then what I should do? Then I will find out the value of stress at any particular location, which is equals to Pxx divided by Ax, right? Pxx divided by Axx, which I can write it as gamma Axx into x divided by 3 into Axx, and which ultimately turns out to be gamma x by 3. And here also the maximum stress will occur at the top fiber. Okay, sigma is maximum. So the maximum value of stress, what it will be? Gamma,
L by 3.
yeah, gamma L by 3. Okay, or we can rewrite this in terms of W also. If I rewrite in terms of W, it will be W by A. Okay, by multiplying and dividing by A. Okay, then coming to the deflection formula, which is nothing but integration of 0 to L Pxx into dx divided by Ae, right? Gamma into Axx into x divided by 3 into dx divided by Axx into E. And here also Axx cancels, and here it will be gamma into L square by 6E. Okay, here if I'm again writing in terms of W, it will be W L by 2AE, similar to what we got there. Here also we got the deflection as WL by 2AE and the maximum stress as W by A, whereas here for conical member also we are getting this value as W by A, and for deformation we are getting WL by 2AE. Okay, the one important thing you can note down here is, like, for example, this delta L is actually gamma L square by 6E, which is actually independent of the cross section dimensions. Okay, The deformation is independent of cross section dimensions. Okay. So now we will come to this problem. Can you solve this problem? Here I am having a fixed support, and to this support, two bars, which is like one bar is of one cylindrical bar is of diameter d by 2, and another cylindrical bar is of diameter d. So can anyone draw the axial, I mean the loading diagram for this, and can you show how the loading diagram will look like? For example, how this also has a self weight of W. Okay, let us imagine the member one has a weight of self weight as W. Okay, which is equals to gamma into A into L, which is equals to gamma into pi by 4 into D square into L. Okay, what will be the weight of second member? Can anyone say? This is the weight of first member. What will be the self weight of second member in terms of W1? Can you say?
Divided by 4.
Yeah, W1 divided by 4, or we will imagine as W. Here, the weight of second member will be W divided by 4. So, can you now draw the loading diagram of this?
Two linear lines with different slopes.
Yeah, two linear lines with different slopes. So here it will start from 0, it will go up to W, okay, and after that it will go to 5W. So what will be the reaction of this support? Can anyone say?
So gamma is rho into G.
Gamma is rho into G, yes. So can anyone say what will be the reaction at say for point A? Can you say what will be the reaction at point A?
Five W by 4.
Yeah, 5W by 4. This is W by 4 and this is W. So the reaction will be W plus W by 4, which will be 5W by 4. Okay. So, so for example, first they have asked for the step bar as shown in figure, determine the elongation due to its self weight. Okay. So first we will determine the, now we have drawn the axial load diagram. This is the axial load diagram for this member. Okay. So first we will find out the elongation of this member 1, and then we will find out the elongation of member 2, and then if we add both these elongations, then we will get the total elongation due to self weight. Okay. So what will be the elongation of member 1? This is of self weight W and this is of self weight W by 4. Okay. So what will be the elongation of this member 1?
WL by 2A.
Yeah, WL by 2AE. This elongation will be only due to self weight of this member 1. Okay. Correct?
Yes.
Yeah, due to self weight of member 1. Okay. So similarly, can we find out the elongation of the bar 2, delta L2, or can you
Fine.
draw the free body diagram of W2 alone? I mean member 2 alone. This, what will happen to this load? Whether this will be acting as a uniformly varying load for member 2, or it will act as some other load.
Uniformly.
Will act as
Point
uniform.
load.
Yeah, it will act as a point load. It won't act as a uniformly varying load. See, because this whole member weight of weight of this whole member 1 will act as the point load for member 2. Okay.
Yes, sir.
Yeah, and then I will be getting a uniformly varying load due to self weight of member 2. So the total deflection of member 2 will be nothing but WL by 2AE. Here W means W by 4. Okay.
Okay.
Yeah. Plus due to this the self weight of member 1 will act as a point load for member 2 as shown here, as shown in this figure. Okay. So this will be for you point load. What will be the deflection? It is like PL by AE, right?
Yes, sir.
Yeah. So ultimately, the value of this will be 9WL divided by 2AE. Okay. So the total elongation will be the summation of delta L1 plus delta L2. Is it clear?
Sir,
Ah, yes.
sir, actually it's getting confused. Like, why it is due to the weight below, and because if you take a point at any section,
Okay.
that point will be deflected. Sorry, it will get elongated due to the weight above it, right, sir?
Okay. See here, what actually we are getting is like, see, we are considering the datum here. Okay. This as the datum. Okay. So gravitational force acts downwards. Okay. So if we are considering this as the datum, x is equals to 0, only due to the below part we will be getting loads at this fiber. Okay, we are not considering the datum here at x is equals to 0 because like I said you the example, right? Imagine your whole body, okay, and imagine you are like what to say, hanging from a pole, okay. So if you whether your toes will be feeling any weight.
No, sir.
Yeah, but the same toes will be feeling the weight if I tie some any weight to the toes of your body. Okay. So based on
Yes.
that logic, I am saying here the weight due to the below section only will be occurring.
So which means the elongation here means the elongation below the section which we consider.
See, here the elongation is actually the total elongation of this entire system. Okay. But for example, if I take any cross section and if you ask what is the self weight as at this cross section, I will simply say as gamma into A into x, where x is measured from here.
Yes, sir.
And if you ask what is the self weight at this bottom tip, then I will simply say it as 0 because below this I am not having any weight.
Yes.
Take the analogy of a human body and you can as I said earlier, right, imagine like your toes to be freely hanging. Okay, when you tie any of weight to your toes, then only you will feel like okay, I'm having some weight below, otherwise your toe will be feeling like I don't have any weight below. Okay.
Yes.
Yeah. So so now we have find out the total elongation due to self weight. Now coming to what will be the ratio of the axial stresses. Okay. So what will be the maximum value of axial stress or on member 1? Anyone?
W by A.
Yeah, it is W by A. And what will be the maximum stress on member 2?
5W by 4.
Yes. So 5 into W by 4. And since here the area is also changing, right? like here you can write this as a by 4. If you are imagining this as a, this you can write it as a by 4. Okay, so a by 4, which will turn out to be 20 w divided by 4, 4a. Okay.
Yes.
Yeah. Here you can see, for example, here I can write this as pi by 4 into d square. So it will become 4w by pi d square. Okay. Here if I am writing it in terms of d by 2 the whole square, then it will turn out to be 20w by pi d square. Okay. Then you can find out the ratio of axial stresses. It can be sigma max or 2 by sigma max 1 or sigma max 1 by sigma max 2. Okay. Depending on the question.
5.
Yeah. 5.
Sir, in the second member, 4 and 4 will be cancelled out, so that will be 5w or pi d square, right?
See, actually here if you write the for example 5w by 4 is the load, okay, and area is actually nothing but pi by 4 into d by 2 the whole
D
square.
by 2 square, okay.
Yeah, so if you write like this, it will turn out to be 20w by pi d square. Okay.
Yes, sir.
Yeah. So let's go to uh, thermal stresses. Okay. And I asked to Yasdeep, and he has taught some basics on thermal stresses. Okay. So what I will do is like I will move to first on the basics of thermal stresses, and then I will solve some problems on like what will be thermal stresses in conical. I mean like for composite bars and for bars in parallel. Okay. So let's imagine like what is the thermal stresses. Okay. So here I am quickly going through the basics of thermal stresses. Okay. Imagine this to be a cubical, I mean a cuboidal thing. Okay, this is of length L. Okay, this is of breadth B, and this is of thickness T. Okay, and this cubical, I mean cube or rectangular slab, I'm heating it uniformly. Okay, uniform heating means like each and every point experiences the same amount of temperature rise. Okay, this is for uniform heating. So the elongation is given by alpha into txx into dx. Okay, this is the value of the. I mean, this is the elongation due to the temperature increase. Okay, this is defined like this. Okay, so here what I have imagined is like the temperature distribution is uniform along this bar. Okay, for example, if I take the temperature distribution, it is uniformly heated up, okay, by T degree Celsius. Okay, and what is the alpha coefficient of thermal expansion? So if I find the delta L along the length of this rectangular slab, I am integrating it from 0 to L alpha into T. Since T is uniformly heated, like T can be taken as constant. Here T is nothing but delta T. Okay, the amount of temperature rise. It is not a particular value, say 20 degrees Celsius or something like that. This is nothing but delta T. Okay, the amount of temperature rise that I am denoting here as T. Okay, and what I will get alpha T into L. Okay, similarly I will be getting delta L along the breadth as alpha T into B, and I will be getting delta L of T as alpha T into T. Okay, this is for a uniformly heated rectangular slab. For example, imagine this rectangular slab is heated non-uniformly, and it is the temperature distribution is uniformly varying. Okay, can you imagine what will be? Can you say what will be the value of delta t here, or the elongation along the length delta L, along the length L, integration of 0 to L alpha t. For t, what can I substitute? Imagine this to be x is equals to 0 and this to be x is equals to L.
Tx by L.
Yeah, tx by L into dx. Okay, so if I'm here, alpha t is the amount of temperature rise. Okay, alpha t by L is constant, and if I'm integrating x square by 2, it will come, and if I substitute, it will be alpha t into L divided by 2. Okay, similarly I can write it for delta b, and I mean delta L of b and delta L of t. Okay, so till now we have discussed about the deformation due to temperature rise, but whether here, for example, this is the case of free expansion. Okay, free expansion means I have not constrained this bar to any degrees of freedom. Okay, all these the sides of all these slabs are free to expand. So whether can I expect any stresses to be generated due to temperature rise?
No, sir.
Yes. Only when I am constraining this along any particular direction, I will get the stresses developed inside this body. Okay, this is clear, right? And the next
Yes,
concept
sir.
which I want to say is like, for example, imagine a circular cross-sectional bar. Okay, imagine this to be a circular cross-sectional bar of diameter d. Okay, and of length L. Okay, and I am giving three such bars. Okay, this is a tapered bar, and this is also of same length L, and there is another cubical or a cuboidal thing. Okay, and this is also of length L, and these all three objects are subjected to same temperature rise. Okay, t degree Celsius, which means like I'm increasing the temperature of all these members by say for example 40 degrees Celsius or 50 degrees Celsius. So can you say whether the deformation along the length, whether it will be same or different for each one of these?
Same.
Yes, the delta L for each one of these will be equal to alpha into t into L. Okay, irrespective of the cross section, like I will be getting the same amount of deformation due to thermal loads. Okay, and also if I calculate the thermal strain, okay, in the x direction, imagine like this is the x direction, what will be the thermal strain? Alpha TL divided by L, which is equals to alpha into T. Okay, up to this is clear, right? Now I am moving to the completely restricted expansion. Okay, this I will quick uh, try to finish it out quickly. Okay, you can imagine this to be a, bar of diameter d. Okay, and I am increasing this temperature of this bar by t degrees Celsius. Okay, so what happens in the free expansion? The same bar, for example, if this is the initial state, it will expand in all directions, right? Yeah, but due to this bar, what happens is like this is actually constrained. Okay, so due to this there will be reactions from this support, and this will be a single value r. Okay, due to temperature increase this will try to expand, but due to the fixed supports, what will happen, this will apply a compressive load on this bar, and the same bar is retained to its original shape. Okay, whereas in the diameter it will try to increase. Okay, getting what I'm saying?
Yes, sir.
Yeah. So the total elongation of this bar will be equal to 0 since this is kept between a fixed support. So this total elongation I can split it up into two components, one due to thermal deformation and one due to axial load, which is due to this R. Okay, which is equals to 0. Okay. So what is the deformation due to thermal load? Alpha into T into L. And what is the deformation due to this axial load?
RL by A.
Yeah, RL by AE.
Um,
Why I have
A.
introduced minus sign here?
Compressive, sir.
Compressive.
Yes. So from this you can get the value of R. Okay, which is equals to alpha T E into A. From this I can get the maximum, I mean the axial stress also, which is equals to alpha into T into E. And minus or plus, or whether it is compressive stress, right?
Compressive.
Yes. Either I should write compressive or I should denote it by a minus sign. Okay. Yeah. So the total strain along the x direction is equals to 0. Okay. Now coming to the y direction. What will be the value of the total strain in y direction? One due to thermal. Okay. And another one, is there any component due to the axial load?
Self weight, sir.
No.
No. Not self weight. Here we are not considering self weight. Here we are considering only the bar or the external loads. Okay.
Yes,
Here,
sir.
whether you can think of any other what to say strain components in the y direction.
Yes, sir.
Poisson's ratio.
Yeah, correct. So due to Poisson's ratio, what will happen? Like you will be getting a lateral strain which is developed in this direction, y direction. Okay. Imagining like this is x direction, this is y direction. Okay. Here I will be getting a lateral strain. Okay. And this lateral strain is equals to, okay, here I will write lateral strain is equals to minus mu times longitudinal strain. Okay. And this longitudinal strain is actually what? Minus mu into,
RL by A.
0.
yeah, I can write it as see RL by AE divided by L I have to write, or else for example if I am going for strain balance in the x direction, what I can write, alpha T due to, alpha T is the thermal strain due to temperature rise. Okay, plus epsilon longitudinal I can write equal to 0. So therefore epsilon longitudinal will be equal to minus of alpha T, which means like I am getting a compressive strain in the x direction. Correct?
Yes, sir.
Yeah. So here what I will be writing is like minus alpha T I will be writing. So here lateral strain turns out to be a tensile strain, a positive value. That is actually that is the one which should happen, right? For example, compressive strain is happening here. You will be getting an tensile strain in the perpendicular directions. Okay. Is it clear?
Yes, sir.
Yeah. So the total strain in y direction will be equal to alpha T, which is due to the strain temperature increase plus mu of alpha T, which is equals to 1 plus mu into alpha T. Okay. This I can rewrite it as, what is the strain? I can write delta D by D. Okay. Is this clear?
Yes, sir.
Yeah. So as of now, I am skipping this the what to say, like yielding thing. For example, if I have a bar like this and if there is a gap between these two, okay, and this gap, let us imagine this to be lambda. Okay, what will be the thermal stress or strain which is developed due to this gap? Okay, whether you want me to do this or shall I skip and proceed to composite bars? It's your choice.
Sir, it is important for gate examination.
Yes, definitely it is important for gate examination.
So you will proceed, sir.
Okay, okay, then fine. So this is the case of partially restricted in one direction. Okay. For example, here I am having a circular bar of diameter d. Okay, and to this bar I am continuously heating, and this is a uniform temperature rise. All the cases here we are considering is of uniform temperature rise, and this temperature rise is actually T degree Celsius. Okay, then the gap between these two is like I am imagining this as lambda. Okay, so what happens is like after the original length I am imagining this as length L. Okay, so after I am increasing the temperature, this will try to expand, and once it touches this, whether I can get any expansion further, no, right, it will be restricted by this support, right, and I will be getting a reaction here. Whether it is clear or not.
Clear,
See,
sir.
yeah, I am continuously increasing the temperature, and once the thermal strain, for example, it will be alpha TL. Okay, if this alpha TL is greater than lambda, then I will be getting a reaction force. Sorry. Okay. So the total elongation which is permitted in the x direction, okay, this is the x direction. So the total elongation which is permitted in the x direction, or the total strain here, I can in the x direction I will be writing as epsilon total in x direction is equals to epsilon thermal plus epsilon longitudinal, okay, which is due to the reactions from the support, which is equals to what, lambda divided by L, which is the permissible strain. Okay.
Yes, sir.
Yeah. So from this, epsilon thermal will be equal to alpha t plus epsilon longitudinal, which is equals to lambda by L. Okay. From this, I can write epsilon longitudinal as lambda by L minus of alpha t, and I can rewrite this as like epsilon longitudinal equal to minus, if I take common, alpha t minus lambda by L. Okay. And this is a compressive strain. Okay. And if I want to find out the value of stress which is induced in this, okay, which is equals to minus of alpha t minus lambda by L into E. Okay, and minus indicates it is a compressive stress. Okay, is this clear?
Sir, strain in thermal plus strain in longitudinal is equal to lambda by L. Please
This one I have
explain
to
it.
explain. This first equation.
Yes, sir. Yes.
Yeah, see, actually, the total strain which is permitted in the x direction is actually nothing but lambda is the change in dimension of this total bar. Okay, divided by the original length is what? L. Okay, so only
Okay, sir. Okay.
so only I have written here is as like lambda by L, which is the permissible strain, and this permissible strain is equals to the combined strain due to temperature rise and due to this reaction force. And due to this reaction force I will be getting a longitudinal strain which is compressive. Okay, so that I don't know how much it is, so that I can find it out using this equation.
Okay.
Okay, and the corresponding stress I can find it out using this equation. Here I have to write compressive. Sorry. Okay, so this is the case of like expansion, partial expansion. Okay, now I will go to thermal stresses in compound bars. Okay, first we will see bars in series and then we will see bars in parallel. Okay, so now thermal stresses compound bars. First, we will see bars in series. Okay. So this topic has not been touched by ESD, and so I plan to take this. Okay. So here we are having a fixed support. Okay, and here I am having two bars. Say this is one bar and this is another one bar. Okay, and this bar is subjected to a uniform temperature rise. Okay, here I am increasing the temperature T degrees Celsius. Okay, so this is made of one material and this is made of another material. So both these things will be having different coefficient of thermal expansion, right? Because thermal coefficient of thermal expansion is a property of a material. Okay, and this will be having separate E1 and this will be having separate E2. Okay, so when I am increasing the temperature, what will happen? This will try to expand. Okay, but due to fixed supports on both the sides, you will be getting a reaction R. Okay.
So the total elongation by both of them is balanced by thermal
Yes, axial or the reaction from the support. The total elongation is balanced by the axial because this can't expand, right? Only see, I am increasing the temperature and this will try to expand, whereas the reaction from the support will try to compress this. Okay?
Yes.
Yeah. So what happens in each member? Can you say what is the load acting on each member? For example, in this member, what is the load acting, and for on member two, what is the load acting on each?
Reaction RC.
Yeah, reaction R. And this is a compressive load. Okay, compressive load is acting on each member. Okay, so if I want to find out the value of stress, it is nothing but for example in member 1 it is like P1 by A1, and for member 2 it will be P2 by A2. Here it will be sigma 1 will be minus of R divided by A1, and if I am ignoring this minus sign, I will write it as compressive. Okay, and sigma 2 will be R divided by A2. So if I take the ratio of this sigma 1 by sigma 2, it will be A2 divided by A1. And this is one of the important relation which you should use. Someone is unmuted their audio. Can you please mute it? Yeah. So sigma 1 by sigma 2 is equals to A2 divided by A1. This is one of the important relation for solving these kinds of problems. Okay. And then I will find out the delta L total. Delta L total is actually equal to 0, right? Since I don't have any deformation in the length direction. Okay? Yeah?
Yes.
Yes. Okay. And this, for example, this delta L total comprises of four deformation components. One due to thermal strain or thermal elongation of member 1, and another one due to thermal elongation of member 2, and another due to axial load, and another one due to this axial load acting on member 2. Okay, so I am rewriting this as delta thermal of 1, okay, plus delta axial of 1 plus delta thermal of 2 plus delta axial of 3, I mean 2, equal to 0. Okay, what is the delta thermal of 1? Alpha 1 T into L1. Okay, imagine these two are having different lengths, L1 and L2. Okay, based on this, I am giving you a homework problem, so you can copy this diagram also. Okay, so alpha 1 T into L1 plus what is the delta axial of 1?
RL1
Yeah,
by
R,
A1.
yeah, R into L1 divided by A1 into E1. So this will be minus sign, right? Because it is compressive. So minus of R into L1 divided by A1 into E1 plus alpha 2 into T into L2 plus minus of R into L2 divided by A2 into E2. Okay. So here if I replacing this alpha T L1 and alpha T alpha 2 into T into L2, this I can take it to the right hand side, right? So it will become R by A1 into L1 divided by E1 plus R into L2 divided by A2 into E2. I can rewrite this R by A1 and R by A2 as sigma 1 and sigma 2, right? So it will turn out to be sigma 1 L1 divided by E1 plus sigma 2 into L2 divided by E2. Okay. So from this, so this is the second relation which is very much important. So from these two relations, you will be given the value of alpha 1, you will be given the value of T, and you will be given the value of L, alpha 2, T, L2, everything will be known. Only thing you have to find out is like sigma 1 and sigma 2. And from these two equations, you have to find. From equations 1 and 2, you can find sigma 1 and sigma 2. And if they are giving another one bar, okay, in series, then you will be getting another one relation, right? Sigma 3 by sigma 2 you will be getting, and sigma 3 by sigma 1 relation also you will be getting in terms of a2 by a3, and here it will be a1 by a3. Okay. And here you will be getting additional terms like alpha 3 at into l3, and here you will be getting sigma 3 into l3 divided by e3. This is for 3 bars in series. Okay. Is this clear?
Yes, yes.
Okay. So, in for example, when the temperature is increasing, what value of sigma 1? See, for example, you will be getting a value of sigma 1 and sigma 2, right? You will be, for example, let us say 80 megapascal you are getting on substituting this. Whether it will be a tensile or compressive residual stress, I mean compressive stress.
Compressive.
Compressive, yeah. Okay. And if the temperature is lowered, for example, if the temperature is decreased for the whole system, and if I'm calculating sigma 1 and sigma 2, what will be, for example, sigma 1 turns out to be 40 and sigma 2 turns out to be 30. What will be the stress, whether it will be compressive or tensile?
Tensile.
Yeah, for both thing it will be tensile. Okay. So coming to bars in parallel. Okay. The same thing I am imagining. Okay. And here I am taking this to be a freely composite bar. Okay. Okay. So this will be made of this hatched region, right? It is made of, let us assume, copper. Okay. And this region, okay, this is made of steel, and this is made of copper. Okay, imagining like you are having a steel steel cylinder inside a copper tube. Okay, and then you are actually heating this whole member. Okay, so here what it will happen, and alpha coefficient of thermal expansion of copper is greater than coefficient of thermal expansion of steel. So here you can say what will happen, and these two are bonded together. These two materials are bonded together. So due to temperature rise, what will happen is like which will try to expand very fast, and which will try to expand very slowly, or which will expand very longer and which will expand very shorter.
Copper will expand
Copper.
longer.
Yes, copper will expand by an amount which is like this, and whereas steel will try to expand only up to this. Okay. So this will be the delta thermal due to 1, and this will be delta thermal due to 2. But the final thing, whether you are expecting like whether this will be of different elongations, or whether these two will elongate and the final cross section will be around somewhere in between.
In between.
Somewhere in between.
Yeah, somewhere in between, because like this expansion due to copper is restricted by an axial or a reaction due to this steel. Okay, and it will apply a compressive stress on the copper. Okay, whereas the same amount of what to say, a reaction load will be applied on the steel, so that it by the copper rod, so that it will try to elongate. Okay. Okay, so the final deformation will be somewhere in between. Okay, so this will be the elongation due to axial load due to reaction force from copper, whereas for copper this will be the compressive or the compressive elongation due to axial load by steel. Okay, so if I write this in terms of equation, can I write the sum of axial deformations? Okay, the sum of axial deformations of copper as well as steel, okay, is equal to the difference in thermal deformations. Can I write like this? This is a very important part in bars in parallel, so you must understand this. Whether can I write like this? Hello?
Sir,
Sir,
both the
will
bar same elongation.
Yeah?
Then sir, copper and steel you are adding both.
Yes, see, for example, copper is elongating up to this, okay, due to temperature alone, temperature rise alone. Whereas for steel, it is elongating up to this, okay, due to temperature alone. Okay, this is delta TH of 1 and this is delta TH of 2, okay, but somewhere the final position is like this in between, okay. So this will be elongation of axial load due to for steel, and this will be compression of axial load due to for copper. Okay. So can I
Okay.
write like this: delta T of 1 minus delta T of 2, which will be equal to delta axial of steel plus delta axial of copper. From
Yes,
this
sir.
diagram, I am taking this formula. Okay.
Okay.
Yeah. So delta axial of copper will be a compressive load, and delta L of steel will be a, tensile load. And similarly, delta T1 is actually alpha 1 and delta T is corresponding to alpha 2. Okay, this is the notation you should follow here. Follow here. Okay, and the other equation comes from the load, which is like same reaction force is acting on both these things, right? So P is constant. Only thing is like A1 will be varying, and for sigma 2 it will be same P by A2. And if I write sigma 1 by sigma 2, it will again be equal to A2 by A1. Okay, this is one equation, and from this we will elaborate here. Okay, for example, the what will be the axial elongation? Can anyone say? Sigma 1 into L1 divided by E1, right? Correct or not?
Yeah.
Yeah. Here both
Yes, sir.
L1 and L2 are same, because this is a composite bar of length L. So again sigma 2 into L2 divided by E2, which is equals to alpha 1 into T into L1 minus alpha 2 into T into L2. And here L1 and L2 are equal, so I am cancelling out all the L's. Okay. And alpha 1 is greater than alpha 2. So what you will be getting here is like a positive value. So from this you will be getting sigma 1 by E1 plus sigma 2 by E2 equals to alpha 1, I mean alpha 1 minus alpha 2 into t. Okay, this will be your second equation and this will be your first equation. So from these two equations you can calculate the value of sigma 1 and sigma 2. Okay,
Okay.
so for example here if I am getting the value of sigma 1 as 40 megapascal and here if I am getting the sigma 2 value as 20 megapascal, what will be the stress induced in copper, whether it will be tensile stress or compressive stress?
So
Compress.
sigma 1 is negative.
Yeah, it will be compressive stress. Okay,
Yes.
because like it will try to expand further but this is restricted by the steel, so it applies a compressive load on copper. Okay, whereas for steel what will be the value or what will be the nature of stress, it will be tensile. Okay,
Yes.
so for example when the temperature is actually increasing, we can conclude like the more the or what we can say the compressive stresses will be developed in a bar which is having a higher coefficient of thermal expansion, whereas tensile thermal stresses will be developed in the bar which is having lower coefficient of thermal expansion. Okay, for example here alpha 1 is greater, right? So for here sigma 1 will be compressive and sigma 2 will be tensile. For heating case alone, for heating case alone, and if I am cooling the whole setup, what will happen? Corresponding to alpha 1 I will be getting sigma 1 as tensile. Okay, and corresponding to alpha 2 I will be getting sigma 2 as compressive. The opposite I will get. Means like for example during cooling what will happen, this will the copper tube will try to I mean compress a lot faster but steel will restrict it. So due to that what will happen, tensile stress or tensile load will be induced on copper tube and steel will try to uh, compress very slowly. So due to that what will happen, copper will induce a reaction force which is compressive. Okay, and due to that sigma 2 will be compressive. You are getting this or not?
Yes.
Okay, so we shall stop here the class here today and from the next class onwards like we will spend some more time on like strain energy like maximum 10 minutes and then we will go for shear force and bending moment diagrams. Okay,
Excuse me, sir.
yep.
I have question for the TT of this classes.
Hmm.
This the TT is only for third week till third week is shown in the website. So what will the schedule from next week?
Okay, that's what the schedule from next week will be like. Next week I will be teaching SFD and BMD.
Sure, it will be updated on website.
Yes, yes, I will update those things. Okay,
Okay.
yeah. So homework problems like I will share you
Sir,
the link. Okay, so you can get the homework problems from there.
Okay.
sir,
Sir,
in
you'll be
equation 2, we have given sigma to both positive. Have we considered them as tensile only?
Here, right in equation two, this is the thing
Ah,
you are
yes, sir.
asking, right?
Yes, sir.
Yeah, that's what. See, here we have considered, for example, on applying this equation, you will be getting one value of stress and one value of strain, right? So that value of strain stresses will both be positive, but you have to make sure like one will be compressive and another one will be tensile based on
Yes,
the
sir.
value of alphas. Okay, if for example in heating case,
Yes, sir. But
uh,
if one is tensile and one is compressive,
hmm,
then that equation may give
no.
wrong
Using this
results.
equation, you will be getting only positive values. That is the first thing. Okay. Okay, if you use this
Okay, sir.
equation, if you use this equation 2, you will be getting only positive value since alpha 1 is greater than alpha 2, right? Correct or not?
Yes, sir. Yes,
Since
sir.
alpha 1 is greater than alpha 2, you will be getting both the values of sigma 1 and sigma 2 to be positive. But in the end, you should write the answer as sigma 1 is equals to minus 40 megapascal, sigma 2 equals to 20 megapascal. Like that, you should write. Based on this, whether it is given for heating condition or whether it is given for cooling condition.
Okay, sir.
Okay? See,
Sir,
Okay, sir.
yes.
sir, kindly show the slide on thermal stresses, sir. I want to take a screenshot.
Okay. Which one? This one?
Yes, sir.
Okay.
Okay, thank you, sir.
Yeah. So this video I will be uploading by today in my channel, so you can also view there. And can anyone say whether this is accessible or not? The link which I have shared with you.
Sir, it is accessible. Videos are empty.
Videos are empty. Yeah, I will add the videos later. Okay.
Okay, sir.
Yeah. Today
Sir,
I
can
will.
you please add the slides as well?
Mostly. Okay. Okay. I will add those slides also.
Sir, can you post once
Sir,
again?
channel name.
Channel name. Okay. Channel name. It is Gate NPTEL. Okay, maybe I will copy the link of the channel name and I will post it in that Google Drive also. Okay.
Uh,
Mostly I
can
will
you,
upload all the videos in that Google Drive itself. You can see from that. Okay.
Okay, sir.
Yeah.
Thank you, sir.
Yeah.
Sir, in the homework problems, some pictures are not there, sir. Loading.
In the homework problems, wait, I will see.
There is, it says below figure, but there is no figure.
Which question can you exactly? Below
This
figure,
one.
yeah, here I have drawn this figure, right? In first problem you are asking, right?
Yes, sir. Is it the same as one in the video which you did?
No, no, no. This is different from that of video. Maybe I will see here in my Google Drive. Okay, these things are not visible.
It is not visible for me. Can
Okay,
Is it visible for others?
no, I think it is not visible for me
No,
also.
it is not visible.
Okay,
No, sir, not possible.
okay, then I will upload it. Maybe you got the link right. You got the link of the Google folder, right?
Yes, sir.
Yes, sir.
Yeah, I will try to
uh,
upload this. Okay.
sir, can you repost it again? I just got
Okay.
lost.
Yeah, I will repost. Okay, I will try to make the changes for the homework problem. Okay. So is this fine?
Thank you, sir.
Yeah.